Welcome to The Explainer. Today, we're jumping into what has to be one of the longest detective stories in history, a 2,500-year-long quest to understand the atom. It's an incredible journey, really, from just a philosophical hunch to literally seeing the building blocks of our universe. So let's kick things off with a fact that is, honestly, just staggering. For nearly 2,000 years, think about that, 2,000 years, the world's smartest people, the greatest thinkers, were just plain wrong about what everything is made of. I mean, it's one of the biggest questions you can even ask, right? What is everything really made of? Like, if you could just keep breaking something down into smaller and smaller pieces, where would you end up? It seems so simple, but that one question, it kicked off a debate that went on for centuries. So, to get to the beginning of this whole thing, we've got to go way back. Our story starts where a lot of these big ideas do, ancient Greece. And you had two brilliant minds who came up with two totally different answers to that very question. Okay, so on one side, you've got this guy Democritus. He had this wild idea that everything is made of these teeny tiny unbreakable particles. He called them atomos, which literally means uncuttable. Then, on the other side, you have the heavyweight champion of philosophy, Aristotle. He was like, no way. He argued that matter is just this continuous, smooth stuff that you could, in theory, just keep on dividing forever and ever. And here's the kicker, neither of them had a shred of experimental proof. It was all just a philosophical debate. But Aristotle's idea that matter was this continuous gunk, it just felt more right. You know? It matched what we see every day. When you cut a piece of bread, you don't see little particles falling out. So because Aristotle was, well, Aristotle, his huge influence meant his idea won. And it didn't just win for a little while. It dominated Western thought for almost 2 millennia. The whole idea of atoms just got pushed aside. All right, let's fast forward a bit, a long bit. We're jumping to the 1700s, and the world of science is totally different. People aren't just satisfied with philosophical arguments anymore. They want cold, hard proof. They want data. And this, right here, is when the first real clues in our atomic detective story start to pop up. So what was the big change? Well, it was an obsession with one thing, measurement. Suddenly, with better tools like really precise scales, scientists could meticulously weigh everything going into and coming out of a chemical reaction. They weren't just guessing anymore, they were gathering hard data. And this was the first real evidence, the first real breadcrumbs on the trail. And what's the first huge clue they found? It was this. In a closed system, matter doesn't just vanish into thin air or pop out of nowhere. If you start with, say, 10 grams of ingredients for a reaction, you're going to end up with exactly 10 grams of products. Nothing's lost. Mass is conserved. The next clue was just as big. Scientists started noticing that pure compounds are like they have a strict recipe. It doesn't matter if you have a tiny pinch of it or a massive chunk, the ratio of the elements inside is always the same. Exactly the same. Take table salt, for instance, a perfect example. It doesn't matter if you get it from a salt mine in Europe or from the shaker on your kitchen table. It is always 39.34% sodium and 60.66% chlorine by mass. Always. That kind of rigid consistency, it just screams that there has to be some kind of fundamental building block, right? Okay, now this next clue, it's a bit of a mouthful, I'll admit. But trust me, it's a total game changer. It basically says that when two elements can team up to form different compounds, think about carbon and oxygen, they don't just do it randomly. They combine in these really neat, clean, predictable ways. We're talking simple whole number ratios. And this is where it gets so cool. So take carbon and oxygen again. They can make carbon monoxide or they can make carbon dioxide. And here's the thing. For the same fixed amount of carbon, the amount of oxygen in carbon dioxide is exactly double the amount in carbon monoxide. Not kind of double, not 1.9 something times, exactly double. A perfect 2-to-1 ratio. A pattern that clean strongly suggests that matter comes in little packets, in atoms. So let's recap. We've got 3 huge clues, 3 laws, all built on careful measurement. The evidence is piling up, the stage is set. All we need now is a master detective to walk in, look at all the pieces, and solve the whole mystery. And that detective's name was John Dalton, an English school teacher. In 1808, he puts forward this absolutely brilliant 5-point theory that just explains everything. You know those simple whole number ratios we just talked about? Bam. Point 4 covers that. The idea that mass is always conserved? Well, that's points 3 and 5. Atoms just get rearranged, not destroyed. Dalton had basically resurrected Democritus's 2,000-year-old idea, but this time he had the receipts. He had hard scientific evidence to back it all up. And Dalton's theory? It was a massive success. I mean, it became the bedrock of modern chemistry. But like any good story, just when you think the case is closed, there's a twist. Yeah, it turns out Dalton made one little mistake, but it was a big one. His third point, that atoms are indivisible? Wrong. The very thing whose name meant uncuttable could, in fact, be cut. The fundamental building block had even smaller building blocks inside of it. And just like that, a whole new mystery opens up. Okay, so if atoms are made of even smaller things, how in the world do you study that? It's not like you can just put one under a regular microscope and slice it open to see what's inside. They're way too small for that. The scientists who came after Dalton had to get really, really clever. The analogy here is perfect. It's like being handed a wrapped present and trying to figure out what's inside just by shaking it, weighing it, and listening to it. You can't see inside the atom, so they had to probe it from the outside, zapping it with electricity, shooting particles at it. And then they'd build a model of what must be inside based on how the atom reacted to all that poking and prodding. So after decades of these ingenious experiments that slowly revealed this inner world of electrons, protons, and neutrons, science was ready for another massive leap. Let's jump ahead to the modern era, because the conclusion to this story is truly mind-blowing. This is where the idea, the theory, finally becomes something we can see. Think about this. After more than 2,000 years of just debating, of inferring, of piecing together indirect clues, in 1981, scientists finally did it. They built a microscope so powerful it could actually see individual atoms. Democritus's ancient guess was no longer just a theory. It was right there, visible. But it gets even crazier. They didn't just look at the atoms. The technology was so precise, they could use the tip of the microscope to pick up single iron atoms, one by one, and place them exactly where they wanted. They arranged 48 of them in a perfect circle on a copper surface. And what you're seeing, that's not just a drawing. It's a real structure. They call it a quantum corral. And those ripples inside, those are the waves of actual electrons trapped inside. It's an unbelievable direct look into the quantum realm. And really, this is the grand finale of that 2,500-year-long journey. We went from simply asking, what is stuff made of, to being able to see the answer, and then, finally, to being able to arrange the answer. This power, the ability to build things one atom at a time, this is the foundation for everything from nanotechnology to quantum computers to revolutionary new medicines. It's literally the stuff that's shaping our future. It is just an incredible story of human curiosity, isn't it? Of persistence and sheer ingenuity. And it really makes you wonder, what are the big, seemingly impossible questions that we're asking today? The ones that feel like pure philosophy. What mysteries are hiding in plain sight that maybe a few centuries from now our descendants won't just be able to see, but will be able to control?